This video, we're going to take a look at ionization energy. Specifically, we're going to focus on the trend of something known as the first ionization energy. First ionization energy refers specifically to the quantity of energy that's necessary to remove an electron from a neutral atom and turn that atom into a positive one ion by having that single electron removed from the outer layer. So once again, the first ionization energy refers to the quantity of energy that's required to remove or strip off a single electron from a neutral atom and turn that atom into a positive one ion. In the chart that we have here, this graph, we can focus on what happens to the energy, first ionization energy, moved from lithium all the way up to here to helium, which is going across the second row of the periodic table. The graph indicates, we can see here the vertical axis is energy, that as we're going across the periodic table from lithium to, neon, across our first row of the periodic table, second row of the periodic table, our ionization energy is increasing and increasing. We see a similar pattern for the third period on the periodic table. As we progress from sodium to argon, the energy increases. So as we're moving across, again, we see the first ionization energy increasing. Similarly, for the fourth period, as we go potassium and krypton, and we see this rubidium to xenon throughout the periodic table. But as we go across, the ionization energy increases. So the general trend that we see here is that we go across the periodic table, the first ionization energy tends to increase. In the second period on the periodic table, all the elements have their outermost electrons at energy level 2, n equals 2. So as we move across from lithium all the way over to neon, one thing we can see is the number of protons in the nucleus keeps increasing. Lithium has +3, beryllium +4, and as we work our way over to neon, as we complete our n equals 2 second energy level, we get to a +10 in the nucleus. We have to focus on Coulomb's law here. F equals K Q1 times Q2 over D squared to help us explain the trend in ionization energy. Also, let's remind ourselves that the trend is that atoms get smaller as we move across the periodic table. Now, focusing on the lithium atom, lithium has a charge of +3 in its nucleus and a total of 3 negative electrons. So using Coulomb's law, the Q1 and Q2 value for lithium, Q1 would be a +3 for the nucleus, Q2 would be the -3 for the electrons. This would create an attractive force between the nucleus and the outer electrons. Moving to the opposite end of the second row on the periodic table, we have a neon atom. Neon now has a nucleus with a +10 charge and now has 10 total negative electrons. This gives us a Q1 and Q2 of +10 and -10, which according to Coulomb's law would create a much greater force of attraction than what we see in a lithium atom. This would be why we would observe that lithium is a larger atom than a neon atom, because of the lesser quantity of attractive force between the nucleus and outermost electrons. Whereas neon, we see a greater force of attraction between the nucleus and the outermost electrons, causing the atom to shrink. We see here, as we move across the periodic table, the nuclear charge of the nucleus gets greater and greater and greater via the addition of additional protons. Therefore, the attractive force between the nucleus and outer electrons gets larger. Therefore, the energy required, right here, our first ionization energy, required to move an electron will increase. Now, as we move down the periodic table, progressing from lithium to sodium, potassium, rubidium, cesium, as we go down the first column here, we also notice that there's a trend here as the ionization energy decreases as we move down the periodic table. So the general trend that we see as we move down a column on the periodic table, the first ionization energy we'll see is decreasing. Moving down the periodic table from lithium to sodium to potassium, the outermost electrons move from 2s in lithium to 3s in sodium to 4s in potassium. Because the outer electrons, 2s, 3s, 4s, get further and further away from the nucleus, the distance that we see between the nucleus and the outermost electrons gets greater and greater and greater as we move down the periodic table. This increased distance between the nucleus and outer electrons, according to Coulomb's law, where we see distance squared in the denominator, if we divide by a larger and larger distance, that's going to cause the force of attraction between the nucleus and the outermost electrons to lessen. Because the force of attraction is lessening, the amount of energy required to move an electron from the outermost layer of the atom is going to decrease. And we see then as we move down the periodic table in a column that the energy required to move a single electron from that outer layer gets less and less and less. Additionally, there's also something as we move down the periodic table known as the shielding effect. As we progress downward, each atom we have more and more and more full inner layers of electrons that block the nucleus from effectively interacting to its fullest with the outermost electrons in the atom. So again, the full inner layers that we see here, and for example, sodium or potassium has a couple layers of inner electrons that are full. Those shield the outer electrons from experiencing the full force of attraction of the nuclear charge. And since the nucleus is being slightly blocked, the overall force of attraction lessens, and we see a decrease in the amount of ionization energy required as we go down the periodic table. Next, we're going to take a look at two kinks that appear in the general first ionization energy trend. One of these is beryllium to boron on our periodic table. The other one occurs as we move from nitrogen to oxygen. Let's first take a look at the beryllium to boron kink in the trend. If we look at lithium, lithium has a single 2s electron. Beryllium completes the 2s sublevel with 2 electrons. And as we go to boron, we see the first electron appearing in the 2p sublevel. The 2p sublevel is ever so slightly higher in energy than the 2s sublevel. Higher in energy means that the distance that we see between the nucleus and the now 2p sublevel outermost electrons is slightly greater. A slightly greater distance between the nucleus and outer electrons means the force of attraction is going to go down slightly. And with that diminishment in the force of attraction, we see the ionization energy required to move this single electron from the 2p sublevel is a little bit less than what we'd see for the 2s electrons, where the sublevel is closer to the nucleus and experience a greater force of attraction between the nucleus and outermost electrons. So we see lithium has a first ionization energy of 520 kilojoules per mole. We see an increase as we go to beryllium of 900 and a slight decrease as we move to boron, and that's because the 2p sublevel is now slightly further away from the nucleus than the 2s sublevel is. A greater distance means a slightly lesser amount of attraction between the nucleus and outermost electrons, so it becomes a little bit easier to remove the single electron that we see here, the first one, in the 2p sublevel. It's a temporary kink in the pattern, because as we go to the next element, carbon, we add in an additional electron in the 2p sublevel. We see the ionization energy continuing in an upward trend. This is because when we go to carbon, we've added in an additional proton to the nucleus, so the 2p, 2s sublevels all get pulled in a little tighter to the nucleus because of the additional nuclear charge with the additional proton that we see in the carbon nucleus. Now let's take a look at why we see a kink in the first ionization energy pattern as we progress from oxygen to nitrogen. The thing that we see in oxygen has our first set of paired electrons in the 2p sublevel. This pair of electrons that we have in the 2p sublevel orbital, they experience negative to negative repulsive forces. These negative to negative repulsive forces between the two electrons that are located in this single orbital in the 2p sublevel actually lessen the amount of energy required to remove an electron. We see this in the data in that the first ionization energy for nitrogen is 1400 kilojoules per mole, and there's a slight decrease in the energy as we go to 1300 kilojoules per mole to remove an outermost electron from an oxygen atom. As we move to the next element to the right on the periodic table from oxygen to fluorine, fluorine has an additional pair of electrons in the 2p sublevel. However, we see that the ionization energy for this continues in an upward pattern. As we go from oxygen of 1300 kilojoules per mole to remove an outer electron, to oxygen it's up to 1700. That's because, fluorine. Fluorine has an additional proton in the nucleus. That additional proton causes all of the sublevels to get pulled closer to the nucleus. We have an increased attractive force between the nucleus and the outermost electrons. Increased attractive force will be reflected by a greater amount of energy required to remove an electron. Completing the row when we get to neon, neon now has positive 10 protons in its nucleus. And we see that we go up to 2100 kilojoules per mole. We still have the negative repulsive forces occurring between the pairs of electrons, but the additional protons in the nucleus draw all the outermost electrons closer to the nucleus as we have a greater internuclear effective charge interacting with the outermost electrons. That greater attraction between the nucleus and the outermost electrons we see reflected by an increase in the energy required to remove a single electron from that outermost layer of electrons. And we see an increase in the first ionization energy.